Okay, so here's a very awkwardly positioned first video. Um, this is my fourth channel. I I forgot what the other three were, um, but I'll be having Albert help me. He's holding the microphone, and this time we're solving a double integral. But we're gonna convert to polar coordinates. Now, normally that would be a nightmare, and you would hate your life if you do that, because I mean, who wants to do polar coordinates? We always work with Cartesians, right? So what we're going to do, well, for this one, now identify for this problem that we have the double integral of cosine x squared plus y squared. Now, if you know anything about double integrals or integrals at all, then you'll kind of see that this would be a really, really hard integral. And you would end up having to do some of these non-elementary complex analysis integration techniques. So instead of doing that, because we aren't that smart and we have a life, we're going to convert to polar coordinates. Now, if you remember the important thing about polar coordinates, it's basically these three things right here. Everything from x and y turns into r and theta, because that's what we'd be integrating with respect to. And now I'll show you everything that you need to change in this Cartesian double integral. Now, first things first, right off the bat, we can automatically see that we have x squared plus y squared inside of the parentheses. So obviously, that's going to turn into r squared, right? Because, I mean, that's one of the rules of translating. So we can automatically write down cosine of r squared, and then we can go ahead and write dr d theta. And for your conversion of polar integrals, instead of just dx dy to dr d theta, for the dr d theta, we're going to have an extra term of r. So it'll be r dr d theta. And so we'll have all of this multiplied by r. And that shouldn't be a tough integral even in this case. So what we have to do is convert our bounds up here. Okay, so we're looking for the bounds, and we saw the bound for the previous Cartesian was negative, or at least for the dy, it was negative square root of 1 minus x squared. At least I think. Let me make sure before I do it. Yes. Okay, so that's that's what y is equal to, right? And so automatically we have to try to picture this in our head. We can't really picture it that well. But what we'll do is square both sides. And so we'll get rid of that. And we're left with y squared equals 1 minus x squared. Add x squared to both sides. And we realize that's a circle with radius 1, right? We could just write that. And so that'll be our lower bound for the Cartesian coordinate. And remember, our original y was a negative root 1 minus x squared. So that means it'll just be the semicircle, the bottom semicircle of this circle. That's a lot of circle, right? And so that's our first part. And yeah, so since we have a radius of 1, or since we just found out our radius is equal to 1, we can go ahead and start with the dr part, right? So it'll be from 0 to 1. That's what we're integrating with respect to in terms of the radius. Duh. Now, the angle is a different story. I don't know why I erased the circle. I still needed the circle. So we have this semicircle with a radius of 1, right? And so the angles here are kind of arbitrary, but whatever. At here, where we would start is at pi, right? And we're going around until we finish at 2 pi. And so that would be our angle that we're integrating with respect to. And so now that you have the bound set up, it becomes a fairly easy integral from here. Now, if you're watching this video, I would assume you have some knowledge of double integrals, unless you're watching the wrong video. Now, the first thing you'll do is, I mean, you could just do this integral first, right? And this, I mean, you're integrating with respect to r, and we have an r right here, and we have an r squared inside of the cosine function. So obviously we're going to do u equals r squared, and then du equals 2r dr. I don't know why I wrote a capital R, but bear with me. And so that gives us our new, if we plug 0 and 1 into that u to change our limits, and we get the same limits. So we'll have 0 to 1 of, it'll be 1/2 cosine of u du. And so this is a pretty simple integral. We just take the integral of cosine of u, which is sine of u, and then we're doing this from 0 to 1. And so sine of 0 is 0. We automatically know that, so we could just ignore that. And then we'll just have 1/2 sine of 1, which is kind of a weird number, but oh well. Okay, and now it's just really, really easy, because this whole thing right here, and we're doing the outside integral, the with respect to d theta, or with respect to theta. And this whole thing right here is a constant, so we can just treat it like a constant. You could take it out if you wanted to, but that's too repetitive. So we'll just add a theta, and then we'll get 1/2 sine of 1 theta from 2 pi to pi. And then we do the math, and we get pi sine of 1 minus pi over 2 sine of 1. And then we just do that simple subtraction, and we end up with pi over 2 sine of 1 as our final answer. And yeah, that would have been way easier than trying to learn complex analysis, because we like our lives. So yeah, I don't know why I started off my first video with Calc 3 if I barely even know it. So the next video will be an introduction to series, and I'm gonna cry.